Thanks, Aaron, for coming to this, probably the only ambiguous talk in this conference. So this is joint work with Peter from Northwestern and Sujoy and Ludovic from Queen Mary. So in this paper, we're going to talk about how to persuade with ambiguous communication. So persuasion, the theme of this session, is where captures the idea that a sender may wish to favorably influence the action taken by some receiver by strategically choosing how to communicate with the receiver. So in the correct literature of Bayesian persuasion, it is often modeled out where the sender can chooses and commits to a statistical experiment, which is a mapping from pair of relevant states to distributions or messages. And the receiver can be modeled as knowing what the sender's choice of the experiment, and then best response to it by choosing a mapping from the messages to distributions or actions. So that is the Bayesian persuasion. In this paper, we're going to study persuasion, but in the same time, we're going to expand the set of communication strategies for the sender. Especially, we're going to allow for the sender to communicate also in an ambiguous manner. So how do we model that? We're going to model that the sender can commit to a mapping from some pair of irrelevant ambiguous events to statistical experiment. So as a special case, Bayesian persuasion is where this mapping is going to be a constant mapping. So all the events map to the same experiment, that is Bayesian persuasion. And I'm going to make more precise in a few slides. So in the same time, the receiver is going to be modeled as knowing the sender's strategy and best response to it, but maybe ambiguity averse. So let me comment on why we focus on ambiguity averse. So first of all, this is in line with a huge literature in decision theory and economics that are motivated by the well-known Alfred paradox. And for those who may not be familiar with that, you can easily think of ambiguity aversion as a decision maker who is uncertain about the underlying property law and may behave in a way that at ease, putting more weight to those outcomes associated with the work outcome. So in this paper, we ask the following questions. So first of all, now given that the sender has a strictly larger set of strategies, can the sender benefit from that? And moreover, if the sender really benefits, so we want to understand when and how such improvement can be achieved. And moreover, we also want to understand what is the optimal ambiguous communication strategy in such a setting. So in this paper, we provide all answers to these questions. But like in short, for today's talk, I'm going to just tell you a simple example to illustrate the main ideas we have. So for this example, it's going to be a two-state uniform prior. The receiver has three actions. So here's the payoff matrix in each box. The first number is the sender's payoff, and the second number is the receiver's payoff. So notice that for action A1, both players believe that omega-1 is a better state action in omega-1, and for A2, both players believe that it's a better action in A2, and the only conflict interest is about action A3. So action A3 is the worst action for the sender because it gives the word payoff in both states, whereas it is the bad action for the receiver instead of omega-1, but worse in action omega-2. So the main challenge for this persuasion game for the sender is to communicate enough information to the receiver to better coordinate the two actions, A1 and A2, with the corresponding state, but should not communicate too much information, such that make diversion for the receiver to find A3 problem, in the case where the receiver believes that the state is very likely to be omega-1. Okay? So I'm going to first of all tell you what is the optimal Bayesian persuasion in this case, and then only after that I'm going to tell you how do I introduce ambiguity and ambiguity aversion, how that might further benefit the sender. How to solve Bayesian persuasion? We know that we're going to zoom pictures. So here is the standard practice. So you have three actions. I'm going to draw three lines. So those are the receiver's expected payoff from these three actions as a function of the property of states in terms of omega-2. And from this, you can see that the upper envelope indicates the receiver's best responses given different probability of the states. And now in the same graph, I can draw the sender's payoff given the receiver's best response, but and a function of the probability of states. And now our good old friend concave tells you that you can draw the concave of the origin curve, and now we know what is the optimal Bayesian persuasion. Because the prior is 1/2, so you can just read through what is 1/2, and that point, that is the value of optimal Bayesian persuasion, and it can be achieved by the following experiment, which we call a sigma BP. So a sigma BP recommends action A1 instead of omega-1 for sure, And instead of omega 2, it recommends action A1 with the property of quarter and recommend A2 with the property 3/4. So once the receiver observes the recommendation of A2, they know that its state is omega 2 for sure, so A2 is optimal. And when they observe the recommendation A1, given this experiment, they are going to be exactly indifferent between the two actions, A1 and A3, so they are willing to follow the recommendation. So we're going to call this receiver obedient when they are facing this Bayesian experiment. Now I'm going to tell you how the defender can further benefit if the receiver is ambiguity averse and the defender can use ambiguous strategies. So as I said, the formal definition of the ambiguous experiment is going to be a mapping, but in fact it's easier or more helpful to think about it as a distribution over statistical experiments given by a tuple with mu theta, sigma theta, parameterized by the parameter theta. So you can interpret theta as an instance of a payoff irrelevant source of ambiguity, where both players perceive that there's some ambiguity with the underlying state. And mu, you can think of it as a probability measure or a belief that an ambiguity neutral player would hold when they are facing this uncertainty. So notice that if the receiver is ambiguity neutral, and when they are facing this ambiguous experiment, what they do, they just calculate whatever the average or the mixture of those experiments, which will be exactly a statistical experiment. So that it will be just the same as Bayesian persuasion. So in that case, in the receiver is ambiguity neutral, there's going to be no benefit from ambiguous communication. So what about ambiguity averse receivers? So in this paper, we're going to use the smooth ambiguity model by KNN to model how the receiver responds, how the receiver's preferences when they're facing an ambiguous experiment, especially when they're ambiguity averse. So the way to model it as is the following. So first of all, at UR of sigma to denote the receiver's expected payoff when they are following the recommendation of that experiment. And then the receiver will evaluate the ambiguous experiment theta by theta or experiment by experiment, and then aggregate it using the property measure mu, but only after applying this phi function, which captures the ambiguity attitude of the receiver. So, and then it's also apply this phi prime just to make everything back to the same unit as utilities. So this phi function characterizes the ambiguity attitude in smooth ambiguity model. For example, at one extreme, where the phi is just linear or even identity, you immediately see that we will just go back to the standard expected utility model. But in the same time, if the phi is concave, it captures the case where the receiver is ambiguity averse. Okay, so how does this effect of ambiguity aversion affect how the receiver is going to respond when they're facing an ambiguous experiment? So we show that the receiver's behavior is actually equivalent to when they're an ambiguity neutral receiver. But when they are facing the ambiguous experiment, they replace the measure mu by this effect measure, what we call, which you can think of as a distortion of the mu of the distribution mu. So then this distortion is going to be distorted by the phi r prime of the receiver's payoff from different experiments. So because phi r prime is concave, so you initially realize that for experiments with a higher outcome, phi r prime is actually going to be lower. But for experiments with a lower outcome, the phi r prime is going to be higher. So the effect of ambiguity aversion here is precisely that the receiver will assign relatively higher weight on those experiments, which gives them a lower payoff, and relatively less weight on those with a higher payoff. And in fact, we show that a key lemma in our paper is that the receiver is obedient when they are facing an ambiguity experiment, going to be if and only if when they are obedient facing an unambiguous experiment given by this effective average of those experiments in the sigma theta. Okay, so that is the effect of ambiguity aversion. Now let's go back to this example. Actually, go back to this graph. So notice that for sigma BP, if the standard wants to implement it, so there's another way of implementing it is by designing this mixture of the following two experiments. Sigma theta upper bar is a fully informative experiment, which recommends action only A1, A2 in different states, where another experiment, which is sigma theta lower bar, which is an uninformative experiment, recommends only the action A1. So notice that a 3/4 and 1/4 mixture of these two experiments will be exactly corresponding to sigma BP. So now the sender can design an ambiguous experiment by choosing this state space such that if from an ambiguity neutral perspective, it's going to be 3/4 of the time, sigma upper bar, sigma theta upper bar is going to be recommended, and with 1/4 of the time, sigma theta lower bar going to be recommended. So if the receiver is ambiguity neutral, the receiver would be as if just facing sigma BP, so they will be willing to be obedient. But what if the receiver is ambiguity reverse? So notice that sigma theta upper bar gives both the sender and the receiver a strictly higher payoff than sigma theta lower bar. And if you still remember the effect of ambiguity reversion, from the receiver's perspective, they're actually going to put in more weight on sigma theta lower bar and putting less weight on sigma theta upper bar. So if the sender chooses mu to be precisely 3/4, from the receiver's perspective, they're actually going to be strictly less than 3/4 from their perspective. And that is a good news for the sender, because the sender would like to recommend sigma upper bar more often. So now here's the trick. So the sender can further push up mu of the upper bar to the point which is strictly greater than 3/4, to the point where, from the receiver's perspective, that is precisely 3/4, according to their effective measure. So that is the key. So in this model, because of ambiguity aversion, the sender can choose a mu strictly greater than 3/4, but in the same time guarantees the receiver's being obedient when they're facing this ambiguous experiment. And especially if the sender is ambiguity neutral, that will give the sender a strictly higher payoff than Bayesian persuasion. So that is the key idea in this example, which how ambiguity aversion might benefit the sender. Okay, so yeah, 6 minutes, right?
Yes.
Okay, so so here is kind of the idea that how you're gonna choose. Once you move mu to this direction, effectively you are moving the effective posterior of the receiver from somewhere that the receiver will find A1 strictly beneficial to the point where the receiver would believe that A1 and A3 are exactly different. So that is how you see that from the graph, which is how ambiguity communication might benefit the sender. Okay, so let me talk about the key takeaways. So in this example, if I have already said that for these two experiments, sigma theta upper bar and sigma theta lower bar, the key is that if the receiver follows recommendation, both the sender and the receiver believe that sigma theta upper bar is going to be a better experiment compared with the other one. So we're going to call this kind of configuration a Pareto rank experiment. And because of this Pareto ranking, it's actually how the benefit for the sender realizes in that example. And in fact, this intuition goes a long way. So in the paper, we show that it is actually a necessary condition for the sender to benefit if there exists such a Pareto rank splitting of some obedient experiment or some obedient experiment that the receiver is willing to follow. So from that, well, that sounds to be a weak condition, but even with that necessary condition, we are able to rule out any benefit from ambiguous communication if the receiver has only two actions. And that is the reason why you didn't see a cross-filter judge example in my talk. So, and by pointing out from this example, and then there's something that is not that obvious, but I'd like to mention here, is that the receiver actually also benefits from ambiguous communication. So we calculate that, in fact, no matter what is the ambiguous attitude for the receiver, their actual payoff from the ambiguous communication strategy is actually strictly higher than what they could get from the optimal Bayesian persuasion, by the ambiguous communication strategy. So the main intuition here is the following. Okay, so here is a sentence that I have to read because here that I cannot remove any word from it. So the fundamental source of gain over Bayesian persuasion is that this strategically chosen ambiguity provides a way for the sender to partially mitigate the conflict interest with the receiver while inducing the receiver to be partially motivated to hedge against this ambiguity. In a way, beneficial to both of them. So in that, it allows the sender to propose more valuable experiments. Okay, so what does it mean? It means that in the example, the sender now has the ability to recommend the sigma alpha bar more often in terms of the ambiguity neutral probabilities, in a way that is because that may previously that is not obedient, that is not essentially compatible with the receiver, so that were not implementable. But because of the introduction of ambiguity and because of the receiver's ambiguity aversion, now after you recommend the same experiment, the receiver may feel that their ambiguity. If they deviate, they're going to face more ambiguity, so they are not be willing to deviate from recommendations. So that is kind of the main intuition we have. Okay, I have 2 minutes for one more thing. So being a persuasion talk, being in a persuasion session, there's something that I have to say. I cannot just walk away without mentioning this. You might be already wondering, yes, we have a computation condition. Yes, so not that straightforward, but yeah, we eventually get it. So we have a computation characterization of, first of all, when the sender benefits from ambiguous communication, and second, what is the optimal ambiguous communication in an arbitrary persuasion game. So the computation characterization we have is not the same as the standard one, because we cannot do it in the standard belief space. But in fact, we can do it is in the space of the experimental space, because we call that our main object is the distribution over experiment. And in fact, it's a splitting of a obedient experiment to all possible common combinations of the experiments. So that is kind of the base probability condition in our framework. Okay, so that's all for you. Thanks. Thanks so much.